Thank you. Thank you very much. Thank you for being here. So wonderful to have you here. I'm so glad to be here in this room with you and having the opportunity to deliver this information once again. And I'm real excited about it because I've got a whole bunch of new stuff to talk about. So I'm going to kind of walk you through a little bit of the way I discovered this information and the way I came across it, my logic through it, and the path I took. And if I walk you through the same path I took, you'll see that it actually is a very simple path. It's a very simple way of thinking. It's very fundamental and very simple axioms that just needs very little adjustments in our current physics and science and so on to generate just a little bit of a different picture that opens doors to a whole new way of being. And so, although this information may seem quite complex, it actually, is very accessible to everyone. And I teach this to 7 years old and to 80 years old, and everybody can get it. So keep your mind open, keep your heart open, and we'll go from there. So it really started when I was approximately 9 years old. I could have been 10 or 9, but I remember very distinctly this first lesson at school. And interestingly, I found that many other people had the same kind of hick when they got into this first lesson. It was the first lesson in geometry. And the teacher went to the blackboard and said, today we're going to learn about geometry, and the first lesson in geometry is dimensions. And I got really excited because I had all these incredible world that I was living in my head, and I had all these interaction with all these other dimensions in my head, and I thought, oh my God, this teacher is going to talk about this for the first time ever. I'm going to have an adult that talks about this, and I got really excited about it, and I got so disappointed. It wasn't at all what I expected. The teacher went to the blackboard and made a little dot. And he placed beside the dot dimension 0D. And said this is a dot that represents a dimension that does not exist. And I was already confused. I'm like, oh my God, this is not looking good. I'm probably going to fail this class because I could see the dot. And he was telling me that it didn't exist. And so already I had a problem with that fundamental axiom. And really, this is so crucial. This is so crucial to our understanding of reality. This very fundamental axiom of dimension bleeds into advanced physics, advanced mathematics, and all sorts of sciences, and really changes the picture of the way we see things if, it's not accurate. So I didn't know all this, but I thought, well, I can see the dot, but if you say it doesn't exist, I'll just go with that. And then he said, well, because it doesn't have volume, it doesn't exist. So if you put a bunch of dots together and make a line, you still don't have volume. We'll call that dimension 1. And that doesn't exist either. And, I just kept on going with it. And I could see the other kids in the class were a little bit puzzled about what was going on. And then eventually, he put 4 lines together to make a plane, called it dimension 2, and said that didn't exist either. It still didn't have volume. It was a 2-dimensional flat plane. And, I could see, he used the example that the cartoons in our cartoon books didn't exist, right? And so I could see a lot of the kids were very disappointed. And then he did something extraordinary, something miraculous, something that even puzzled me further. He took 6 planes, put them into a cube, and called it 3D, and said that dimension exists because it has volume. And I could see that everybody was like, okay. There was a problem in logic there. Turns out that I found out much later that Buckminster Fuller had exactly the same problem in his schooling, in his first lessons in geometry. There was a problem there because if you have a dot that doesn't exist, that makes a line that doesn't exist, that makes a plane that doesn't exist, then you cannot get existence out of 6 non-existing planes. So what you get is some unknown feature that could only be called non-existence to the 4th. Not existence. And so here, fundamentally, there's an issue. And that issue has to do with our understanding of how reality emerges, how dimensions are generated, and how we can get existence, reality, atoms, objects, things in space, and how we solve the equations that describe how these things in space come through, how they get here. That is very fundamental. I didn't know all this at the time, but I knew that this principle that was being demonstrated to me was not quite correct. There was definitely improvements that had to be done to it. And I really felt like I didn't want to spend another day going through my life not knowing what a dimension was. So I decided I was going to solve this. And, I had this long bus ride going all the way back home. It was like an hour and a half from that school. And the reason for that is because I kept on getting kicked out of the schools that were closer to my home. So I kept on having to go further and further. And somebody told me, a physicist told me once, that I was furthering my education that way. And he was right, because I had all this time to think in the bus. So I was in the bus and I was thinking about this problem, and I decided I was going to solve that problem before I got out of that bus. And I didn't realize that this problem had been discussed and worked on by many philosophers throughout the ages and so on, all the way down to the Pythagorean schools. I just wanted to solve it right there and then. And so I was thinking, and the bus was getting fuller and fuller, and I was getting hotter and hotter, and it was really, becoming uncomfortable. So I closed my eyes, and in my mind's eye, I escaped the bus so that I would feel more comfortable. And I start to see that the bus would, as I rose above it, the bus would become a dot. And then I rose further, and I saw the earth becoming a dot. And then I rose further, and I saw the solar system becoming a dot. And I rose further again, and I saw the galaxy becoming a dot. And then I start to fly back into the galaxy, into the solar system, back to the earth. And I located the bus I was in, and back into that bus, and back into my body. And I opened my eyes, and I looked at my hand, and I thought, oh, maybe I could fly into my hand. And then so I closed my eyes again, and I thought of flying into my hand, and I saw that inside my hand would be dots that are called cells, and then inside those cells I would see millions and millions of other dots that are called atoms. I probably didn't even know what an atom was at the time. And I continued in and I saw, the nuclei of an atom that was made out of smaller dots and then again smaller dots and so on. And I thought, and then I got it. I had this moment of illumination. And then in the bus, going back from school, oh yes, the only solution to this riddle, the only way you can solve this, the only way you can, the only way you can visualize, understand dimension is if you make the exact opposite axiom right from the beginning, which is that the only thing that exists is the dot. So here, within the dot is all dimensions. Within the dot, we have all the structure of space-time. Within the dot, all possible other dimension became in existence. That's the way I saw it. Meaning that if we continue to divide the dot, we could find smaller and smaller and smaller dots, and those would be like scales of dimensions. And that the only thing that exists is the dot. And it is only from your perspective that you define the scale at which you observe those dimensions. I mean, that was a completely different view, definitely. And I thought, well, if zero dimension is all dimension in one, then that would mean that everybody that I'm looking at in this bus has all the dimensions, all the structure of space-time compactify in every dot. I mean, I wasn't thinking in terms of space-time, but I was thinking in terms of fractal dimensions. I didn't know fractals, but I had defined it in my head. And I got really excited. I was walking on a cloud. I got up in the bus and I didn't know what to do. I was like, oh my God, I think I got it. Everything is a dot. Every dot has infinity within it. Everything can be divided to infinity. And there's dots to infinity, infinitely big, infinitely small. We're living in a big dot that has little dots in it and little dots in it. And I was seeing dots everywhere. It was really exciting. And when you have a revelation, you want to tell someone, right? So I didn't know who to talk to. I wasn't going to talk to the bus driver, and so I ran home when I got out of the bus, and I was waiting for my mom to get back from work. And when my mom came in the door, I'm like, Mom, I figured out something at school today. It's really exciting. And, my mom was so excited because she thought, oh, my God, you finally are doing good at school. Oh, my God. And then I started to tell her about this. And I'm telling my mom, I think you have a dot inside of you that has all the dots and infinite dots inside and all this. And my mom is looking at me with a look of despair. The look of an Italian mother in despair. There's a force in that hasn't been calculated yet. And so she kind of could see it, but she knew it wasn't part of my curriculum at school, and she told me that. And she said, if you answer that in your exam, it's probably not going to go well. And she said, anyway, right now, I just worked 8 hours, and I don't feel infinite. And when she said that, it rang a bell. I mean, she made a point. She made a very important point. I stopped and I had to think about it. It's like, well, if it's true that infinity is compactified in every point, how is it that we have finite boundaries? How is it that things are not just falling into each other to infinity? And how is it that things exist? How do we define those boundaries? How do we have a finite space in an infinite potential? How can that be together? I didn't know at the time, but actually I was tackling one of the fundamental difficulties in advanced physics. The difficulty of dealing with infinities and singularity, which is really the crux of unification at this time. It took me back. I had to think about that one. I was like, oh, I got to go back to the blackboard. I got to think about this before I talk to anybody else. But eventually, it came to me. And it took a very long time. I was much older by the time I realized. But all the way through my childhood, there was a few things that came through to help me deepen my belief that I had found something very crucial. Was I the first one that came to these conclusions? Have these ideas been around before? Absolutely. Okay? Other people have thought about this. Even our, Big Bang Theory says that everything came out of a point the size of a Planck's distance, which is extremely small, billions of times smaller than an atom. These ideas have been around. Have they been well understood? Maybe not. Certainly, I think some of the masters and some of the advanced beings that have walked the earth may have understood them. In terms of physics, in terms of advanced sciences, it's been thought about, but it hasn't been mapped out. It hasn't been understood in its detail in order to be able to apply it to our current physics and our current math. Why would we want to do that, though? Well, we would want to be able to if we want to be able to understand the fundamental structure of creation, and that fundamental structure implies or involves infinities and finite boundaries all at once, we have to find a way to bring these two together, to understand their interaction, to understand how that works. And if we did that, and if we did so, we would have the key to universal forces. We would have the key of the powers of creation. It would be very powerful. It would be powerful for philosophical reason, and it would be very powerful for application to advanced science and technology. Now, it took me a while before I realized that there is a direct and intricate link between infinities and finite boundaries, and how to understand them and how to demonstrate it. I found eventually that the key was geometry, the very thing that got me going in the first place in my geometry lessons. And I'm going to demonstrate to you right now, in very simple terms, that you can create infinities in the confine of a finite boundary. That these are not opposite concepts, but they actually are complementary. There is infinities to create finite boundaries, and there's finite boundaries to create infinities. And in order to demonstrate that, I'm going to use a very simple initial graphic. Although this graphic is simple, it is still absolutely accurate to the geometry that we will see throughout the day today. It's not something in left field. It's something that's very important. So here we're going to do this. We're going to generate a finite boundary we're going to call a circle here. And this circle could be a 3D sphere that contains a very specific space. And in that sphere, or in that circle, we're going to put a triangle, an equilateral triangle. Now, the universe is polarized. And the reason why things are polarized is because they spin. Okay, things in the universe are polarized because they spin. Angular momentum creates shafts of rotation that generates polarity. So if you have polarity, then you can accurately have a reverse triangle in that sphere or in that circle. Now, right away, we have one of the most common ancient symbols that we find all around the world. It's called the Star of David, or the Seal of Solomon, or the six-pointed star. We'll talk about this later on in the presentation, but just take notice of it. Now we can continue to add triangles. And now we get smaller stars, baby stars of David. Okay, baby six-pointed stars. We can continue to add other resolution of stars by adding more triangles. Again, smaller stars of David. Every time we create a new resolution, we can define a very specific boundary. This is very important. And here we find a third boundary, so smaller and smaller sphere. We can continue to make smaller and smaller resolution of this geometry. And in fact, if I give this to my computer as a computer code, and I got it to make geometries maybe 5 resolution deep, and then zoom in, and then go 5 resolution deep again, and then zoom in, and then keep doing that, it would continue to do that to infinity. As long as the computer had power and chips would keep working in there, it would continue to make boundaries for thousands of years. However, I would never, ever, ever exceed the first boundary that I've set for myself. Within a finite system, I've demonstrated to you right now that you can create infinite numbers of division. Infinite numbers of sets of information. In a boundary is the possibility of infinite division. And thus, infinities and finite structures are complementary. Why is this important? Well, if you were taking these principles and applying them to yourself, you could start to visualize, you could start to imagine, you could start to experience that maybe within the confine of the finite structure that you're in is the potential of infinite division, the potential of infinite amount of information. Philosophically, that has a very powerful impact on someone's consciousness. It just happens to be very similar to what many of the masters that have walked the earth have talked about. That within is God, the kingdom of heaven, infinite boundaries, and so on, or infinite potential, and so on. It definitely has an impact on science. Why does it? Well, I'll give you an example. When we discovered biological cells, we had microscopes that were at the maximum of the power of amplification that we could get at the time, and we thought, my God, this stuff is so small, it's gotta be the smallest thing that the universe does. And then we discovered an atom. And there's billions of atoms in every cell. That is extremely small. And we thought, oh, that's gotta be the smallest thing the universe does. And then we discovered protons and neutrons in the center of the atom. We discovered the nuclei of an atom, and we thought, that is so small. That's gotta be the smallest thing the universe does. And then quarks and so on. And what I'm saying here is that every time we find a new boundary, we think, that's it. We found the fundamental structure of creation. The universe goes to that size and then quits. That's it. I'm done. I'm not going smaller. This is way small enough. We did exactly the same thing in the other direction. Right? We thought, at first we thought the Earth was the biggest thing, and then we thought the solar system was the biggest thing. Then we found galaxies. Oh my God! That's got to be the biggest thing, right? And then we found superclusters and so on. Now we're at universal size, and we think, okay, that's it. It stops there. Right? Well, what if it doesn't? Now, what does it mean to the physicists? Well, it means that we've been building accelerators to break particles into smaller and smaller and smaller bits. And now we're at like billions of times smaller than an atom. And we're calling these accelerators, they're serious pieces of machinery. The one that's being built in Switzerland right now, the Hadron Collider, is costing $300 billion. It took 5 countries to flip the bill for that one. And now we're looking for the X bosons and mini white hole black holes. And I'm like, well, at that point, you're dividing the vacuum. And basically, what I'm saying here is that instead of looking, and I'm not the first one that have said that, famous physicist Jeff Chu said it in the 70s, maybe instead of looking for a fundamental particle, we should start looking for a fundamental principle of division. And that's what I came to, is that instead of looking for a fundamental particle, we should start looking for a fundamental pattern of creation. Because if we understand the pattern, then it doesn't matter at which resolution we are observing the identity. We understand the principle behind the identity. Now we have the key to creation. And that would change a lot of things of the way we do physics and the way we think of the universe and how it creates and how it subdivides. I was really excited about this. I started to really study physics. I started to look everywhere to find how things work and where standard physics was at the time. Where did we go, and where did we go wrong, and what needed to be changed to make it do that, to make it look that way, so that we could find that fundamental structure of creation. I was determined that I was going to find this in my lifetime. It was a big mission, you know. And so I went at it, and I started to study a lot. And now we're going to jump forward to me in Georgia Tech. I'm at Georgia Tech, Department of Physics, with the director there and other physicists. And this is an impromptu private meeting discussion with those guys. And basically my sponsors at the time brought me there to measure up with the biggest and most respected physicists, some of the biggest and most respected physicists in theoretical physics. And, you know, I'm there and they have equations everywhere and we're talking about things, and it's a very small meeting, you know, but there's a few students and there's a bunch of physicists there, and there's me. And the only thing I got with me is this book. It's called Gravitation. It's like the Bible of relativistic physics. And it's called Gravitation because when you pick it up, you know, you can really tell gravity is acting upon things. And I was, you know, going through the equations with them, and I'm talking about all this, and I'm really, you know, going through it with them, and I can see that there's a certain amount of irritation, and there's a certain amount of impatience with me, because I'm asking very simple, fundamental questions, and everybody there is doing very advanced, you know, string theory physics and all this, and you know, I'm always going back to like some fundamental things, and they're like, my God, what is this guy doing here, kind of deal. And, you know, and so at one point, I pulled out my book, Gravitation, and I said, okay, after all these equations, which is a few thousand equations, on the metrical structure of space, and then applied to the universal size and so on, the model of our universe at this point, and correct me if I'm wrong, is that the universe is expanding like a balloon. And I opened the book on page 219, and I pulled it out, and I said, here's the picture of what we believe the universe is doing right now. It's expanding like a balloon, and the balloon has little pennies glued to it, and the pennies represents galaxies. That's the standard model. And the galaxies are moving away from each other as the balloon expands. And everybody's like, yes, Nassim. Where are you going with this kind of deal? Like, if you don't know this, go back and study, come back in a few years. And at one point, well, I'm saying, well, okay, I understand this principle. However, I have a question. Out of all these equations everywhere, what I want to know is, where is the equation that represents who's this guy? And the whole room became really silent. And I could see that in the look of the students and the other physicists that there was a look of despair and stress, because sweat was a little bit beading. And I could tell that they got worried because they thought, oh my God, this guy, he might just start talking about God, and we're at Georgia Tech in the physics department. We can't do that. and I reassured them very quickly. I started to draw, and I said, well, you know, let's draw the rest of the guy. And what I'm trying to point out here is that in order for the balloon to expand, then the lungs of the person that's blowing into it have to contract. For every action, there's an equal and opposite reaction. Okay? One of the first laws of physics. So, if our universe is expanding, then there must be something contracting. There must be some compression happening in order to get expansion. There must be a feedback between the expansion and the contraction. And that was my first clue to the relationship between the gravitational field and the electromagnetic radiation. And as well, it applied to my experience in life, because really this is all based on my experience in life. When I was 11, I started meditating. My family came in contact with a young master of meditation that was 14 years old, and I was 11. And he taught me how to meditate, and when I meditated, it felt like I was turning my senses inwards and going towards the center of my existence. I was going towards the middle of my being. And I came, out of that, I found a logic in which there was an internal universe and an external universe. There was something going in and something going out, and the two generated boundaries. And that boundary is what we experience as reality. The thing is that in our society, the tendency is to spend a lot of time analyzing what's out and very little time analyzing what's in. Not only in our, social norms, but as well in our physics and the way we do things. We explode things. That's how we build technology. Our concept of advanced technology is to put a bunch of fuel in a cylinder, put a bunch of people on volunteers on top, and light the bottom and see if they survive the experience, It's all based on expansion, on explosion, on radiation. Very little is based on contraction, on going towards the center, on implosion. And to me, there had to be a direct relationship. So I was really pointing that out. And now we're going to go back to when I was younger. And when I was thinking about that, I could see that this relationship would generate some kind of field equation, would generate some kind of metrical space that I could describe in mathematics, in physics, that would resemble more like a feedback of creation. Well, just happens that the fractal structures that I was talking to you about when you divide space are based on feedback equations. I went to my first chemistry class. And can everybody see this? And the first thing I asked in my chemistry class is, I want to know what an atom is. The chemistry teacher said that was, not in the curriculum of my first chemistry class. And he said that would be a physics question anyway. And as far as I know, we don't quite know exactly what is an atom. And that was quite disappointing for me. But he knew something about atoms. He said, there's one thing we know about atoms, that they're made out of 99.99999% space. And that kind of blew my mind. I was like, wait a minute. So what we see as creation, all the things we see, are mostly made out of space. But they don't feel very spacious. I mean, it's pretty solid. But what's going on is that there's all these fields interacting, and they don't necessarily are in perfect resonance and they make boundaries and so on. And so it feels like it's solid, but it's mostly space. It's basically a field dividing the vacuum. And I thought, oh, there it is. It started to match. And that was my first chemistry class. It started to make sense. Oh, yeah. Maybe we should look at the vacuum. Maybe it's the vacuum, what we call space, that has the key to creation. And the space divides itself, and then we see it as finite boundaries. Maybe the space is the infinity, and the boundary is the finite structure. The field is the finite structure. I started to see it in my head. I got very excited. And later on, I studied vacuum and, understanding of quantum theory, and I realized something. I realized something very important for the evolution of the thoughts I was having. I found that present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formerly be infinite, if not removed by renormalization. Now, renormalization is kind of what they tried to do to me at school. It didn't work so good. But what it means is that when physicists start to look with the tools of quantum theory at subatomic particles and nuclear interaction and all this, they found that in order for this to be happening the way we see it happen, the vacuum density at the quantum level would have to have infinite amount of energy. That was the result of the equations. Well, equations that ends with infinity are very uncomfortable for physicists. There's two kinds of technical words in physics to describe infinities. There's one that's infinities that are normal infinities, and that's usually an infinitely small quantity. Two infinities, right? One is an infinitely small quantity, so it can easily be discarded, right? It doesn't really matter. 0.0000 somewhere down there, it doesn't matter. Okay? That's one kind of... Then there's another very highly technical term you find in physics documentation called nasty infinities. Nasty infinities are infinitely large infinities that creeps up in your mathematics, in your equations, in your conceptual physics. And those are thought to be nasty because when they creep up, it's not like you can just make like it's not there. It's an infinitely large quantity. You can't just sweep it under the carpet and avoid the whole thing. Well, they did a real good job at avoiding this one. But in general, it was not accepted as a valid theory if your theory breaks down into infinities at its results. And so instead of discarding the concept, they did something that they called renormalization. They used the infinite potential of the vacuum and basically took the Planck's distance and took the 10 to the, was 1.616 multiplied by 10 to the minus 33 centimeters. So that's a very, very, very small dot. Notice, though, that the 1.616 is very close to the 1.618 of the phi ratio. And they took that distance, like that very teeny point, which is now billions of times smaller than the nuclei of an atom. And they said, well, that is fundamental to creation. And if we put the number of these little dots in a centimeter cube of space, of vacuum, we will have a finite density for the vacuum fluctuations, for the vacuum density, the energy in a vacuum, in a centimeter cube of vacuum. So here it is. They took a centimeter cube of vacuum. They took a Planck's distance, bitty teeny point, and they stacked them into that cube. And then calculated how much density of these quantities would there be in there to get a finite number. The result is 10 to the 94 grams per centimeter cube. 10 to the 94 grams of centimeter cube. That's 10 to, with 93 zeros, following it. It's an extremely large number. When I'm dealing with a number that large, and it came from a renormalization, my tendency is to think that we're talking about infinities. Okay? Because if you want to get an idea of what density that means, imagine you have a centimeter cube of space that has all of the stars in the universe condensed into it. Like all of the stars we see with the Hubble. Okay, all the galaxies, everything we see, we just put it all in a big trash compactor and we just squash it all up into a centimeter cube of space. All right? Imagine how bright that would be in one way. But never mind that. Then you still wouldn't have the vacuum density. You still would be short from the density of energy that is calculated to be in the vacuum at the quantum level. That is a lot of energy, folks. And so, how did this infinite amount of energy divide and create subatomic particles and atoms? To me, that was the question. To me, maybe the vacuum energy had structure. Maybe the vacuum energy wasn't just a random fluctuation like this, but had a boundary fractal structure, had a geometric structure to it. I didn't know why at the time. I didn't know how I could prove that. I didn't know how I could describe that. But I wanted to explore that thought. I started to see that maybe, just maybe, everything we see in the universe is just division of that energy density of the vacuum in various scales. To me, there was some logic to it. Well, that brought me to eventually a meeting with Elizabeth Rauscher and a collaboration with her. Elizabeth is a very respected physicist that has received medals of honor for her work in black hole physics in the 70s, has worked with John Wheeler, many other very famous physicists. And Elizabeth and I got together, and Elizabeth had written very advanced computation and mathematics for a unified field theory in the 60s and then in the 70s. And she could never kind of get the whole key put together. And, when we met and I talked with her for almost 3 days, I was able to fill in a lot of things, but she didn't know, and we had to talk some more, and we had to run some calculations and all this. And she was definitely skeptical, but we started to write things, and then we thought, well, okay, if this is true, then if we look at a large scale in the universe, we should start to see very specific divisions. We should start to see structure. If the vacuum is dividing under very specific structure, then we should be able to see it. we should be able to calculate it from what we observe. So we decided to write a scaling law. And this is what came out. This is a paper that's unpublished at this time. I'm publishing other papers in the scientific journals right now that are the foundation of the change I've made to Einstein's field equation. This will follow. We presented this at the American Physical Society in Albuquerque, and here and I've presented it as well to some of the directors of the telescope here on the Big Island, and many other astrophysicists and physicists. And usually I get a pretty good reaction out of it. It's kind of, jaw-dropping. What we did is we took the radius of objects, okay? And so here on the in the x-axis is the radius. And here is the frequency of these objects, the fundamental frequency of these objects in hertz. And the energy level of the object is pretty well described by its frequency. So you could think of its energy level as well. If you take the size of the universe, that is, if you look at the way the universe is expanding, you can extrapolate its size. And if you look at all the matter that's in the universe, when you place that amount of density, when you place all that matter in Einstein's field equation, the result is that the universe is too dense for light to escape it. That is, we live inside a black hole. And, that was expected from me. I thought that earlier, and then I realized that as well from my own calculation before, and I thought that would make sense. Because remember, I was thinking that if for every expansion there's an equal and opposite contraction, then everything can be divided to infinity, then everything would have infinite density at its center. Everything would have what we call singularity at its center. And so I thought everything is just a different size black hole. And so I wasn't surprised about this. So we placed the data point for the universal, the 10 to the minus 17 is the universal frequency based on our calculation, and the radius is 10 to the 28. And then we place the next data point for quasars. We're taking average size and frequencies of quasars. This is a very large scale, so it's acceptable. And we place the data point. And it surprised us. It was a fairly good linear progression from universal size. Then we place the data point for galactic centers. So we're getting smaller in scale. And again, an average galactic center oscillation rate and radius. And we place the data point, and again, linear progression. Then we place a data point for solar dynamics, stellar dynamics, and we got a linear progression again. That was astonishing. I mean, there is nothing in standard views that would predict that, other than the view I was getting that the vacuum is dividing itself under very specific structure boundaries. Then we went all the way to the atomic level with the radius and fundamental approximation of frequency for X-ray emission. And we got a data point that was a perfect linear progression again, but this time across the boundary of quantum theory into the atomic level. So now we went from cosmological object to quantum theory level. and this is one of the fundamental fracture in our current physics. Quantum theory and relativistic physics don't agree. They don't work for each other. So that was really exciting. And then we went all the way down to the Planck's lengths and placed the Planck's length dot data point and at 10 to the minus 33. And sure enough, the progression was perfect. And that got us very excited. I mean, definitely it supported what I was trying to explain to Elizabeth and our discussion, and we started to really get some steam going, and it was really exciting to see that happen. And we thought of publishing it, but I wanted to publish first very fundamental physics to be able to explain this, not just the phenomenon. The other thing we noticed is that if you take the distance between the data point, which is kind of nice, it's sweet, and you divide them, you always get very close approximation to the phi ratio. The phi ratio is 1.618 and is, and goes to infinity. It's typical to find it in nature everywhere. You find it in flowers and shells and pine cones. You find it in the way tree divides. You find it in your body. There's a phi ratio between the end of your finger and the second part of your finger, and there's a phi ratio between the second part and the third part and your hand, relative to your fingers, and then your fingers and hand relative to your forearm, and your whole body is built like that, and so on. And so you find it in nature everywhere. So to find it on a scale that's so large was very exciting, because it supported that this would be something that nature would naturally do. That space, that the vacuum would naturally divide itself under these very specific fundamental mathematics, because we observe it in nature everywhere. And so it confirmed to us a lot of it. Now, this was my presentation at Albuquerque, and I'm going to add a little data point for our benefit here. I didn't do that there because it could freak out a few physicists. So the physicists in the audience, please don't freak out. But if you actually add a data point for the biological resolution, what I call the biological resolution, that is the size of the sphere of our cells and their frequency level. Now, this research has shown that there's definite resonance match at approximately 10 to the 11 for the frequency of lipoprotein of the boundary of cells. So that means the cell's boundary, all right, the surface of cells in the biological level oscillate at 10 to the 11 hertz. I mean, that's a massive oscillation. And it's funny because when we think of biology, we always think of some really kind of glooby, kind of blobby thing that's moving really slow, right? But actually, the surface, when you look on the surface oscillation of these cells, it's very intense. A lot of energy. And it just happens that if you take 10 to the 11 hertz and you take the radius of a cell and you apply that much energy into that radius, if you solve that with relativistic physics, the cell obeys the Schwarzschild condition. That is, the cell obeys the condition of a black hole. Okay, I'm not, don't panic. It's okay. But what I'm saying is that we're still dealing with the same fundamental dynamics, even at the biological level. And certainly, there's not any biology in Einstein field equation, and there's no biology in quantum theory. And, this link to biology has been looked for a very long time. Well, we were happy to find that if you place that data point for the biological cells on the graph, it would bisect the graph approximately in the middle of the graph. That is, the biological resolution is the link between the large and the small. You are the event horizon, loosely termed. And you are the data transfer boundary from the extremely large to the extremely small. Isn't that what you do? You gather information and transfer it to your internal self, which in this view has infinite boundary potential. Thus, you're transferring that information through your boundary to the infinite of the universe within yourself. And as you start to see yourself grow into that world, your worldview, your way of being in the universe, the way you are, how you are, completely changes. Because you start to see the importance of your observation. You start to see the importance of your interpretation of the field and what you are feeding the universe. Instead of seeing yourself as an insignificant little dot that means nothing to the universe, you start to see yourself as the center of creation. Now, you might think that's arrogant. I think I've heard something along those lines from the new Pope or something. But I would like to say that if you have come to these conclusions, you must have come to these conclusions finding out that everyone else is the center of their universe as well. And thus, we are all equal, and we're all one. But beyond the philosophical views, the fact that the biology would fit on this graph, the fact that we could start to see the information feedback loop between the radiative side and the contractive side starts to open a whole new field of physics. For 20 years, and I've been saying this for a long time, I've been saying that information doesn't just flow into black holes, but flows out of black holes as well. And I got in a lot of trouble for that. And it was nice to see that just recently, Stephen Hawking has made a public announcement that he now believes, after 15 years of refuting this, or 30 years of refuting this, that black holes have information radiating out, coherent information. Before, they only had Hawking radiation, which was thought to be generic and incoherent. So now this is actually coming to the forefront. It's very exciting for me because finally I feel like there is some support. It was very recently that these announcements were done, and as well, to me, it was clear very long time ago that if this was true, then the center of all galaxies had to be black holes. So I predicted that, and then eventually they found that that was the truth, and although I got in a lot of trouble for saying that early, and so on. And so I start to see the infinite potential of everything present in everything. Okay, so now we've got divisions in the vacuum. What dictates those divisions? How is the vacuum structured? If the vacuum is divided in very specific ways, then it must have very specific division structure. Then the vacuum has structure. How can that be? And what would be the structure? I wanted the key to the equation of vacuum division. I wanted the key to the creation of these boundaries. Because if I knew the key, then I could create one of those boundaries. Now, let's go back in time a little bit, and I'm in high school and I'm not doing so good. I'm still not doing so good in the educational system. And it's funny because my father worked with Piaget and is well respected, child psychologist and so on. And he had all sorts of trouble with me. And at the age of 16, I'm done with the whole thing. And if I have to live doing something else, then that's what I'm going to do. And I decided, since I was a good skier, to become a ski instructor. I was in Alberta at the time, and then eventually in BC, in Canada. And I'm getting tired of it because I'm freezing every day. And I'm tired of freezing every day. And I want to do something else than sit on a cold chairlift. So at the end of one season, I decide, listen, I'm a good scuba diver. Maybe I should try teaching scuba diving in the summer so I don't freeze all year round. So I opened the map and I just pointed. And my finger landed on this island called Isla Mujeres off the coast of Cancun in Mexico. I pulled out my Spanish dictionary and translated Isla Mujeres, and it said Island of the Women. And so I was a ski instructor, so I was like, oh, I'm there, So I got to Isla Mujeres and I started teaching scuba diving, and I'm having a good time, and I get a few days off, and it's like, okay, let's go and visit, ancient sites and stuff, something. So I get out there in the buses with the pigs and the chicken and everything, and I'm going through the jungle, and then I come upon these pyramids, Chichen Itza, just out of the jungle, these huge pyramids sticking out, freaky. And I, went and visit, and so I'm taking pictures of the pyramid, and I climb up the stairs, and at the top is shaded, so I'm happy to get there. And I'm sitting in the shade, and I'm kind of doing a little meditation, try to feel something. And I hear, tour guide coming up and with tourists. And I'm listening to what he's saying in the background. And he's talking about how these people move these stones from the quarries that are miles away across the mountains and down and so on, and then brought those stones and put this pyramid together, and how they use copper tools to carve it and all this stuff. And I'm listening to all this, and it's freaking me out because it's like, I remembered the lessons I had at school about antiquity and so on, and the pyramids of Egypt and so on, and how improbable those theories seemed to me. But, I'm listening, and he's talking about cutting stones with copper tools. I know that copper doesn't cut stone and so on. And I'm having a really hard time with this whole thing because I'm looking at the dense jungle around me, and I'm like, wow, how did they get those rocks here? And then he talks about how precise this pyramid is and how it's aligned to the solstice, so that when the shadow hits the corner of the pyramid on that very specific day, it casts a shadow that generates the body of a snake going down the stairs with the head of the snake carved at the end. I've got a pretty good notions of engineering and astronomy and so on, because I've done a lot of study in that, independent studies. And I'm listening to this, and I'm thinking, whoa, man, this is not easy. You can't just whip that out. Or you can't just have the pyramid built and then, like, on the right day, just get Joe to pick it up and align it. Little bit to the left, Joe. That doesn't work. Can't do that. So I'm listening to this, and I'm kind of confused, but I'm interested. And then I start to think, well, wait a minute, I'm looking for a fundamental structure of creation, and there's these buildings, these pyramids everywhere around the world, and I'm thinking, well, why are they all building pyramids? Why did the Egyptians, the Mayans, the Incas, all these people are building pyramids? What's with pyramids?
Thank you for joining us today in Crossing the Event Horizon. Nassim Haramein's research is supported by the generosity of the public. To directly participate in this most crucial work, see our website for more information on how you can stay involved by visiting www.theresonanceproject.org. Thank you for continuing to spread the word about this exciting work and recommending this DVD to your friends and family. Be sure to watch the special features portion of this DVD.
I had come to my own conclusion earlier on. I had thought, well, because I was a ski instructor and I climbed as well a lot. I love climbing. And I was in nature all the time. I thought, well, if I want to know the structure of the vacuum, if I want to know the structure of space-time at the vacuum level, and if nature is being directed by that structure, I should be able to observe nature and see it. I should be able to deduct it from a good observation of nature. So I was always looking at snow crystals, and when I was climbing at the crystals on the rock, and I was always looking at things and the way branches divides in a tree and all this, and I had come to conclusions that the universal forces, the vacuum division, seem to always generate a very fundamental, specific geometry, and that geometry was the geometry of a sphere. It makes spheres, little spheres, and bigger spheres, and then assembles them together and gets all sorts of things. But I was thinking, wait a minute, though. The sphere would be the part that's on the outside. The sphere would be the event horizon. The sphere would be the boundary from which things radiate. What I want to know is what's inside that. I want to know what's the geometry that holds the sphere together. How does the sphere pop out in the vacuum? And it wasn't obvious, but I started to study geometry and I realized that the sphere is the most unstable geometry. It's got the most surface and it doesn't have structure, so it's the most unstable geometry. So how would it hold together? And I thought, well, it has to have the most stable structure in the middle. And not only would have to be the most stable structure in the middle, whatever the structure was that was holding the sphere, that was dividing the vacuum, that structure had to be in perfect equilibrium. Because it had to be able to be observed as the vacuum. That is, if it had infinite amount of density, at the end of the day, when all the density, all the vectors of the geometry would collide at that level, the geometry that would result would have to be in perfect equilibrium so that we would think that it's empty space. That we'd think that it's a vacuum. So all that logic had come through, and so I started to study what would be the smallest, the most stable, the most equilibrium geometry I could find. And what I had found is that the exact opposite of the sphere, which is the largest and most unstable, was the tetrahedron. And if we look at a tetrahedron, it's made out of, it's the smallest volume possible, okay, with equal edges and equal faces. And it's made out of 3 faces on top and 1 on the bottom. So 4 faces generates, it's like a pyramid with a triangle base. And this is actually the most stable, fundamental, and the most fundamental geometric structure we can find in nature or in geometry. So I thought, well, okay, it probably has something to do with the tetrahedron inside a sphere. And I had come to those conclusions. So I didn't know why all these ancient people were building pyramids. But I thought maybe when I go home, I'll study it and research a little ancient text and stuff like that. So I go home. I'm living in Whistler, right? And I, went to my local library, which wasn't much. I mean, this is a ski resort. And I'm looking around, and this book pops out at me, and it's called Mystery of the Mexican Pyramids by Peter Tompkins. And I thought that was an appropriate title because I really felt there was some kind of mystery going on there. So I pulled out the book and I opened it randomly, if there is such a thing. And it opened on page 280, I believe. And it had this graphic on it. A tetrahedron inside a sphere. This was the first time I was starting to study ancient texts, and that's the first thing I found. Actually, the solution that I had come up with my own logic and my own geometry and my own math on my own. So I started to read, and I got the original papers, and I realized that this graphic came from the result of a 20-year investigation of the plaza and the pyramidal structures that are found north of Mexico City. And it has the moon pyramid, the sun pyramid, and the person that did the survey there, did it for the Americano Society, is Hugh Hollison Jr., I believe. And he came to very amazing conclusions. First of all, when he started to map the whole city at Teotihuacan, he found that the sun pyramid and the moon pyramid and all the other buildings seems to be in appropriate relationship to each other, so to reproduce a map of the solar system, including Pluto and Neptune, which were planets that we didn't discover in modern age until the early 1900s. So that was very amazing to him that these people would have that knowledge of that. It was very compelling. And he started to, he spent 20 years there surveying the whole thing, and he started to find that there was very specific ratio relationship between the buildings and how they were placed and mapped and all this around the world and around the whole city. And he thought, there's some kind of fundamental code that's being used here to build all this. And maybe there's some kind of fundamental message. And after 20 years of research, he delivered his papers to the American Society. And in it, he mentions that according to his mathematics and the way he mapped this, it seems that everything seemed to be pointing out that we should be looking, or that the mathematics that they used had to do with a tetrahedron inside a sphere. This really stunned me. It was amazing. I mean, I thought I was going to copyright that stuff, and somebody had come up with it a few thousand years before me. It was right there in this book, and so that really got me going in studying ancient texts. But more importantly, at the time, there was a comment that was made in that book that the fundamental equation that Hugh Holliston Jr. used to map this out match a very specific mathematics of Buckminster-Fuller, which related to an isotropic vector metric. And the isotropic vector metric is made out of 20 tetrahedrons. There's 10 on the bottom, 6 on the second level, 3 on top, and 1 on top. It's actually a 4-frequency isotropic vector metric. This fundamental geometry was part of Bucky's concept that the universe had a mathematical geometric blueprint to it, so something very similar to my thoughts, and that blueprint related to this very specific metric. So I got very excited and I started to study it in detail. I looked at it in different angles, and I started to think, well, okay, so if I'm not dealing with just one tetrahedron, then there must be the interaction of the tetrahedrons may have different geometries involved in it. And since I was really investigating the structure of the vacuum, I was very interested in the negative space between the tetrahedrons. So I eliminated the tetrahedrons from the space and extrapolated what was in the middle of it, in between the tetrahedrons. And what I found is that what's in between the tetrahedrons is octahedrons, right? Now, an octahedron is a double bonded pyramid, okay? Emphasis on the word pyramid. This is the cavity between the tetrahedrons of the isotropic vector metric. Can everybody see them there? They're tilted like this, okay? And you could think of, for instance, if we look at this top one of the points of the pyramid is up here, the other point is back here somewhere, and it's on an angle somewhat like this, right? For you guys to look at. Everybody sees that? Oh, not quite, like this, right? Okay, so I was excited. Oh, here's the pyramids. It kind of linked with the ancient concepts. Okay, well, that's interesting. And then as I kind of traced all the vectors of the pyramid and in my drawings and in my head, I didn't have a computer at the time. I realized there was some strange negative cavities inside the isotropic vector metric. So here's our isotropic vector metric, and here's the cavities that I noticed that were inside it. Now, if there's 20, so let's put it this way, and if we look in between, there's our octahedrons, okay? But in red here, we've demarked that actually there is another set of tetrahedrons in the middle that are pointing inward, that are pointing down, right? And that are rotated from the initial metric. When I found those, I was surprised because this is thought to be an isotropic vector metric. I thought that must be the same everywhere. There shouldn't be any asymmetry. And certainly, I was looking for the geometry of the vacuum, So I was certainly looking for something that was in equilibrium and couldn't have asymmetry in it. So I was surprised. I didn't know what to do with these cavities in the middle. They didn't belong to the octahedrons, and they didn't belong to the tetrahedrons that were pointing up. So I thought, well, there's one thing for sure, is that if the universe is polarized, it cannot be that the geometry of space would have only one polarity of the equation. It would have to have both sides of the equation, and I had to add the reverse metric to it to get the polarity, the male, the female, the plus, the minus, the white, the black, and so on. So I added another metric below it, but when I did so, if I put one metric base to base to the other, if I put another one base to base to this one, then I have another problem. And that is, I don't get a sphere. I get an egg-shaped structure. And I was looking for the sphere. So this was like a chicken and an egg problem, and I was very confused. I was spending a lot of time on this. I'm walking you through things that took years because I was working to survive at the same time. Eventually, I quit my job, sold all my ski equipment so I could move into a van and sponsor my own research with very little cost. And so I was in my van thinking about all this. I didn't have a computer. So I've got these matrices in my head spinning, and I'm doing all this stuff with them. And I don't want to distort the geometry of the metrics. I'm not wanting to push them into each other. So I'm resisting that idea, and I'm trying to figure out how they would work. And then eventually, I came to it. I did push one into the other, which took me a while because I had to render all these vectors in my head. And I realized that when they would be in perfect relationship to each other, then I would get a perfect sphere. However, what got me extremely excited is that when I pushed one into the other and rotated so that it would be in perfect polarization to each other, the central red space that I didn't know were for what were exactly in the right position to accept the reverse metric without having me distort the geometry or remove tetrahedrons or anything like that. So that the polarized metric would actually be incomplete without its better half. And that when the second metric was inserted into it, it would take exactly the spot to create perfect symmetry at the center. And I was really excited because I was looking for perfect symmetry equilibrium. So I started to render in my head what is the geometry of these tetrahedrons coming in the middle. And that's when I realized that the result of the two metric intersecting with each other to create the perfect sphere generated in the middle what is called a cuboctahedron, which is 8 tetrahedron coming together, which was called by Buckminster Fuller the vector equilibrium, the only geometry in which all vectors are in equal proportion to generate perfect equilibrium. I had found the geometry of perfect equilibrium from the polarity of the two isotropic vector metrics coming together. Why is this geometry, for instance, the only geometry that's in perfect equilibrium? Well, I studied a little bit and I realized that actually, if you have vectors of forces and you want to create equilibrium, then you would have, obviously, now, this vector that just popped out could express a force. And we'd say that that force has this specific unit, which relates to the length of the vector. So bigger the vector, stronger the force, smaller the vector, smaller the force. If you wanted equilibrium, you'd send another vector in the exact opposite direction, at the exact same length, and you'd get equilibrium. However, this would be a very precarious equilibrium. Nature could not use that equilibrium because any distortion would make the vector collapse. Any forces in any other direction would break the equilibrium. So it was very unlikely that the universe used that type of equilibrium. Well, what would it do? Because this is unstable. What would it do? Well, if you were trying to get an equilibrium yourself, you would probably say, well, I'll just keep adding vectors. Well, if you add vectors at 90-degree angle from the initial vectors, you're still not going to get equilibrium because now what's going on is that the edge vectors are longer than the vectors to the center, so they're stronger, it implodes, it doesn't work. No equilibrium. So what would you do? You probably continue to add vectors, and you would probably put them at 45 degrees from the initial one. And now you have another problem. That is, the edge vectors are shorter than the vectors to the center. Now the geometry explodes. Is still no equilibrium. So what would happen is that you would have to make sure that the geometry's edge vector and vectors to the center are the same length. And the only geometry in which this happens is like the snow crystals, the hexagon, where the edge vectors are the exact same length as the vectors to the center. And if we made a 3D hexagon together, we would get a vector equilibrium, which is made out of 12 vectors radiating from the center and 12 edge-bounded vectors that maintains the structure in perfect equilibrium, or 8 tetrahedrons coming together, all right, to create, a vector equilibrium. So 8 of these coming together to create a vector equilibrium. And so that was really telling. That was really exciting for me. I knew this had to do with what I would have to deal with even if you think in advanced physics, for the physicists here, that, of the structure of space, you could think that the vacuum state is going to infinity. At one point, it would have to reduce to the minimum amount of vector for stability. And that would be 12 vectors. So that's the fundamental, basic geometry of equilibrium. But it actually didn't fully work. That is, I still had points on the edge of my metric here. Right? I still had vertices on the edge of my metric that had holes in it. Right? So there was a symmetry. This middle structure with the 2 isotropic vector metric was completely filled, but the edge was not. So I had still asymmetry. I still didn't have equilibrium. So I started scratching my head some more, and I thought about it, and I thought, okay, well, my only solution is to continue to add tetrahedrons until I get equilibrium at all levels. So I continued to add tetrahedrons. I covered the spaces that were open on the edge of the metric. So I had to add 3 tetrahedrons to every edge, which was 8. So that generated 24 more tetrahedrons. So remember, there's 20 tetrahedron in one isotropic vector metric. 2 makes it 40, plus 24, added up to 64 tetrahedron grid. And that's when it came to me. At 64, it all came together. Why is that? Because when I put those added 24 tetrahedron in my head as I was visualizing all this in my van, I realized what I had done. I realized that I had generated a vector equilibrium in the middle, but now I had generated a larger fractal vector equilibrium on the edge. And so now I had a metric that was growing from one vector equilibrium to the other, to the other, to the other. And interestingly, they grew in perfect scale of exactly half the radius, so in harmonic scales or in octaves, if you want. And it was a three-dimensional fractal. This is actually one of the only true three-dimensional fractal I believe exists. And it grew radially, which is what I needed for the radiation part. And then I realized something even more significant, is that the fractal growth could be generated from 8 star tetrahedron. So one star tetrahedron is 8 tetrahedrons coming together to make an octahedron in the middle. Everybody sees that? 8 star tetrahedron, 8 stars like that coming together, okay, to create the vector equilibrium. Right? So 8 of these coming together to create the vector equilibrium. And when I realized that, I saw that the star tetrahedron is 8 tetrahedron pointing out, and that the vector equilibrium is 8 pointing in. And now I had both sides of the event horizon, the radiative side and the contractive side, all in one mathematical metric that was producing both to generate the feedback of creation. I was really excited then. I mean, people would, anyway. My van was bumping around, and it's not because I had a girlfriend. And so so I realized this, and it was like the 8 star tetrahedrons coming together to create the vector equilibrium in the middle. Just like this. And when the whole thing was put together, it would generate a vector equilibrium in the middle, right? The vector equilibrium in the middle. And then it would generate the next fractal vector equilibrium on the outside. Right? And so it was a radial growth generating scale in the vacuum. So I was really excited. I thought I found something very significant. I was looking now to solve this and in terms of physics. How does it apply? How does it, emerge in the physics? And as well, I was starting to think, well, this physics must have, angular momentum, must have dynamics to it. This is not a static thing. This is a fluctuating thing. So how does that all compute? And, I was doing research in advanced physics and all this. I came across a graphic on the internet of a phenomenon that's called crop circles. And that graphic was a perfect representation of the fractal structure of space I had just described and found in my van jumping around. Now I know that there is hoaxes out there and hoaxers out there, and I know they make crop circles at night with their gumboots and drinking moonshine and stuff. But there is as well a lot of genuine phenomenons that goes on with these crop circles, where it's not obvious to just write it off as people jumping around with gumboots. Or Doug and Dave out there, having a good time. What got me really interested is that there was a bunch of croppies, people that photograph these things and measure them and all this, that had gone into, they figured out if somebody is trying to talk to us, whoever that is, maybe we should just try to talk back. So they got some gumboots and they went in there and they stomped around in big letters in their field. What do we need to know? And the very next crop circle that came out was this. And that really, struck a chord with me. And if you look carefully, you can see that the way the crops was laid, it made an effect of light and shadow in which you could see the vectors of the tetrahedron that would be creating this metric in three-dimensional space. Now that's not obvious to do in the middle of the night, in the middle of a field. Alright? This is not a small thing, it's a large thing, and it's very, very accurate. And then, a few weeks later, they seem to insist on the pattern. Another one, just like the first one. And this one, with another set of information in the middle. In this case, there was another set of fractal division that was going on in the middle. And when I looked at it closely, I realized that that set of information was the exact same structure of division, those triangle divisions of space, or these tetrahedron division of space, but in this case, pointing in the opposite direction, going inwards towards infinitely small. Never mind the fact that if I overlaid the octahedron part of the 64 tetrahedron grid over top the crop circle, it was a perfect fit. This compelled me to continue to study these things, and as I was studying advanced physics and continuing to advance my theories, and I realized that there was eventually crop circles that were perfect representations of the 64 tetrahedron grid that were emerging in the crops of England. And then vector equilibriums coming out of the crops of England with singularities at their center, including the information about the boundary generated by the tetrahedrons, so that if you knew that each tetrahedron generates its own boundary, then you would add them here and generate this other geometry which has been popularized as the seed of life. And then a crop circle to tell you you've decoded right. And so this was like a code that was being given. I was very excited about that. I continued to study it, and there was very much information that was coming out of the crop circles that had to do with fractals, the way those spheres, each boundaries of the tetrahedrons divide. Here we can see it in another crop circle where the central part of the sphere divisions it has these crescent that seem to indicate rotation, angular momentum, which is what we're going to get into in a minute or after lunch. And then that division of space was fractalized over the field. And then eventually even structures like this that showed these spheres dividing in a rotational pattern. This one, crop circle, right across from a very well-traveled highway which has Stonehenge on the other side. Okay? Very large crop circle that appeared. And then even larger ones, like so, that showed that spiraling division of space, that dynamic. And now I was starting to really link into I believed I had found a fundamental structure of equilibrium for the vacuum state. Now I had to understand the dynamics that fundamental structure generated in the field equation, the dynamics of it, not the static view of it, but the dynamics of it, the angular momentum, the rotational part of it, the field equation that emerged from it. Because remember, the vacuum state geometry would be the structure that goes towards infinitely small, that collapses into singularity. There's the other side of the equation, the feedback, which is the radiative side, which has all these energy levels and all these dynamics in it, and that had to match to the geometry of space. From this seed, how would the field get generated? I had the static model of the structure of the vacuum, but that was only the vacuum state moving towards infinity. I didn't have the vacuum state generating the electromagnetic radiation from that division of the space. And so I started to, realize that they had to be angular momentum, they had to be spin involved in the space-time manifold to generate that boundary. In order for the vacuum to generate a boundary, it had to have some kind of shearing, and in technical terms, this is called shearing modulus, that would divide the space, that would fracture the structure at very specific intervals. And I was thinking about it, and I was studying, and then eventually it came to me, and I realized, and it came to me in different ways. I realized that they had to be gyroscopic reasons. They had to be gyroscopic dynamics of the angular momentum of the metric of space. And I started to study gyroscopic effect, angular momentum and Coriolis forces and all this. And I started to study deeper and deeper in physics and especially in Einstein field equation, how we dealt with rotation and angular momentum. And I realized that in many cases, we in general try to avoid spin and angular momentum. We try to make things freeze up so that they can get simpler and easier to map out. But when we do that, then we most likely lose a very important component. And then I realized that we had done that with something very, very fundamental. And I started to study how Einstein came to his equations and how his equations were solved. So Einstein did this. He basically, in general relativity, he extrapolated that gravity may not be an internal force of an object, but instead the force of that object applied to the structure of space-time itself. And the way you can describe it simply, imagine a surface of a trampoline. And that trampoline has a big ball, a heavy ball on it. Now the surface of the trampoline around the ball is going to curve like this. And that you could call space-time curvature. And if you took another ball and you put it in the trampoline, it would want to rotate or roll or have an orbit around that first ball because of the space-time curvature around it. This is the typical visualization that you get from space-time curvature. When Einstein wrote this idea of this metric curving and creating this space-time curvature, he didn't solve it. He just threw out the idea, basically. And he published it, and he thought it's going to take a while before this is solved because it's really complex. But there was a German physicist on the Russian front that got a hold of his paper. His name was Karl Schwarzschild. And he thought, hey, let's try solving this. So while dodging bullets and being sick and everything, he solved Einstein field equations. And when he did so, he simplified the equations, he simplified the models so that it would be easier for him to do a first approximation. And the way he did that is that he assumed that the object had no angular momentum, no rotation. Okay? So he solved the equation for something that's not spinning. Because it was his first approximation. He sent the result to Einstein, and Einstein was so impressed that it was already solved, that a solution had already been found. He right away sent it to the Prussian Academy and got it published. And so that was the first solution to Einstein field equation, and it's called the Schwarzschild solution or the Schwarzschild radius. The thing is that when the Schwarzschild radius was solved, when Einstein field equations were solved for the first time, the result of the solution was nothing else than a black hole. Okay? That is, when he tried to solve the solution to calculate how much gravity something produces, you had to have infinite potential in the middle to solve it, meaning it creates a nonlinear infinite potential at the center. His equation predicts black holes. And that's why right away there was talks about how this equation could predict something like a black hole. But, at the time this was highly theoretical, and nobody had ever thought that they would actually come across a black hole in the universe. So everybody basically ignored that part of the equation. And said, well, we can use the weak curvature to predict, the curvature of light around the sun, or how something would land on how much planets or how much galaxies, they rotate and how they're organized. Now, this was very interesting, that the high curvature of the equation was never truly fully acknowledged, because when you approach the center of the equation with the curvature of space-time, the equation of Einstein goes towards infinity. So remember I was telling you everything is a black hole because it's divisible to infinity? Well, here you have Einstein field equation telling you that it is so. That in fact you need that singularity in the middle in order to even calculate the weak curvature. And basically what we did is we used the weak part and we just let go of the other part unless it was called a black hole. What I'm saying here is that first approximation had no rotation and predicted black holes. Okay? So eventually, with Elizabeth Rauscher, we wrote a paper. This is the title of the paper, The Origin of Spin, a consideration of torque and Coriolis forces in Einstein field equations and grand unification theory. This is a paper that's in peer review right now. It's a result of what I'm talking to you about. This is a new solution to Einstein field equations. Okay? There was a solution that was given to Einstein field equation after Karl Schwarzschild. it took a very long time. It wasn't given until 1965. In 1965, the Kerr and Newman solution was rendered, in which you had a black hole, or the object was allowed to spin and have charge. So it had spin, angular momentum, and charge. And it took all the way from Einstein writing these equations to 1965 before that was able to be figured out. So you can imagine the complexity, and this is basically the solution that's mostly used to interpret what we see around stars, black holes, galaxies, and all this. There's a problem though. When you take these solutions and you apply them, for instance, to a galaxy or to the universal size, the result of the equation does not match observation. Okay? The result of the equation only predicts 4% of what we see out there. Alright? That is, in order for the universe to look the way it does, or for a galaxy to look the way it does, with the amount of mass that we are seeing in that galaxy or in the universe, and when we put it in the Einstein field equation, it doesn't match. What they have to do, and what they've done, which I believe is a complete cop-out, is that they've added the 98 or 96% of the mass that's missing and the energy that's missing. They called it dark matter and dark energy. It's very, very convenient. Instead of revising the equation, they assume that it's something out there that they cannot measure and that they cannot see. So that's very convenient, because who can tell them it's wrong? Right? They've been looking for dark matter and dark energy since then. I mean, it's been, almost, at least 10 years of, funding and detectors and all sorts of experiments to detect dark matter and dark energy. Now, I think they will detect something. However, I don't think it's gonna be what they think it is. I think the error is in the equation. And the error in the equation is describing, if this error would be corrected, would describe something that's out there, but that's not dark matter or dark energy. It's only a force that allows these dynamics to happen. And that force, I realized, had been omitted. And I'm going to show you how I found that out. I studied the Kerr-Newman solution that had finally added rotation into the space-time, so that if an object was rotating, they could calculate that as well. The thing is when they did so, they wanted to get rid of complexity as well. Because angular momentum and gyroscopic effects are so complex, they did something very strange. They decided to eliminate the gyroscopic effects of rotation, like eliminating Coriolis forces and torque and things like precession and all this. Well, how would you do that? Well, the way they did this is that they attached the frame of reference to the rotating metric so that there would be no force. Now, this is a little trick that's used in physics and that really tweaks the results. And because this is buried under enormous amount of complexity and very little people on this planet understand these complexities, it is not being noticed until now. Now, what they did is this. Imagine this. You've got a shaft that's turning, maybe on the lathe here, right? or maybe there's a V8 motor spinning this shaft, right? And it's spinning at 5,000 RPM, and you're in front of it. And in a moment of illumination, or in a moment of extreme stupidity, you grab on to that shaft. All right? With all your might. Well, you're gonna experience some effects. Okay? Those effects have to do with shearing, like your skin flying off, heating, like smoke coming off your fingers, all sorts of effects like this that are certainly uncomfortable and that have to do with the force of torque applied now to your hands, right? That's forcing that shaft to spin. All the 300 horsepower of that V8 motor is spinning that shaft. Well, if I grabbed you at the exact moment that you went to grab that shaft, if I grabbed you on your center of gravity and spinned you at the exact same rate, you would feel no force. You would feel no effects in your hand. It would be stationary relative to you. You see? However, I could still say that I'm accounting for angular momentum because I could count the turns that you're going around. So I would have a frequency rate of angular momentum. You see? And that's what they did. Why did they do this way? It actually goes all the way back to a fundamental assumption that was made. That things are spinning in a frictionless environment forever. That is, the assumption is, because if you ask a physicist, what is making the Earth spin? They'll tell you it's because it's in the solar system that's spinning. Then you say, well, what's making the solar system spin? They say, well, it's in the galaxy that's spinning. Well, what's making that spin? Well, that's in the supercluster. Well, what's making that spin? Well, that all started in the Big Bang. You see, son? If it had the Big Bang... Sorry, I'm being cheeky. There was the Big Bang, and then all the energy through everything spinning, and it's been spinning in a frictionless environment since then. So we don't have to account for spin because it's inherent to the Big Bang. First of all, that doesn't tell you where the energy came from to generate that moment of impulse, but certainly it's a very, very large generalization because when you look around, we just happen not to be in a frictionless environment. I mean, it's the same thing at the atomic level. They tell you that electrons spin perpetually because of being in a frictionless environment. They got spinning at the Big Bang, and they're still spinning now at 99.9 something the speed of light, right? Those electrons. Now that's a lot of spin for a long time. And when you look out there, it just happens that it would be true if there's only one atom in the universe. But as soon as you have two atoms, now you have interacting fields. You have friction, you have collision, you have all sorts of things happening. Gravitational fields acting on each other. Not only that, in order for that statement to be true, then all objects would have to be solid, true and true, homogeneous, which we know they're not. For instance, the layers of the sun rotate at different rates and have huge amount of frictions between them. Think of the inside of the Earth. Is the inside of the Earth spinning in a frictionless environment? I don't think so. It's spinning at a different rate as the surface, obviously because we're getting a magnetic field resulting from a dynamo effect. So what's making the inside dynamo spin against the mantle? You're talking molten lava, not frictionless. Not frictionless at all. solar winds in our solar system, the gravitational pull of the Earth. You see, here I have 2 eggs. And don't worry, I'm not going to throw them at you guys. That would be a first. The presenter throws eggs. Bad crowd. Here I have a hard-boiled egg. Fairly, constant density through and through. Okay? Here, an unboiled egg. High level of viscosity in the middle. Okay? I'm going to spin the hard-boiled egg on the floor. Now imagine this hard-boiled egg was in a frictionless environment, or a very low friction environment. It could spin, oops, let me try that again. It could spin constantly and homogeneously as it does here and slow down, but that's mostly because of friction on the floor, right? Now let's imagine that it was frictionless, but you could see how that could be possible. But now, let's try to spin an egg that has high viscosity at its core. It stops very quickly. Most of the angular momentum is absorbed by the viscosity of the central core of the egg. Galaxies are just like an unboiled egg. It has all sorts of density, plasma density change, all sorts of friction, and all sorts of different levels of viscosity, and so is the center of the Earth. There is actually currently no appropriate geological description on how the moment of inertia of our inner core of the Earth occur. How do we get a magnetic field, and what's spinning that dynamo in the center of the Earth? Did you guys have bicycles when you were kids that had those little dynamo on the wheel that created enough current to put up a light in front so you could see at night? Well, in order to spin the dynamo, you still have to pedal. So there's got to be somebody pedaling. There's got to be something forcing things to spin. The new solution that we wrote detached the frame of reference from the rotating metric so that we have an appropriate description of the physics at hand. And the result is that you have torque and Coriolis forces applied to the system directly from the space-time manifold. So let's go back to the analogy of Einstein's field equation of the trampoline curving to generate gravity. So basically Einstein said gravity is the result of space-time curving like the surface of a trampoline. And basically what we say in this paper is that yes, and when space-time curve, it doesn't just curve, but it curls, just like water going down the drain, and that generates spin, angular momentum. And that's the source of the spin of all things. And that is an appropriate way to actually describe physics of angular momentum in the universe. So when we add torque to space-time, the solution gives us a very different picture than a perfect sphere. It generates a torus structure, okay, which is a sphere with 2 holes in the middle at the north and south pole. And because it has Coriolis forces are the forces that makes water rotate in one direction in the north hemisphere and in the other in the south hemisphere, that makes hurricanes rotate in the opposite direction, that makes plasma dynamics on the sun rotate in the opposite direction. Because Coriolis forces were added to the equation, so what we did is we added a term for torque and the Coriolis forces as a secondary rank tensor on the space-time manifold. The result is a double torus structure, a double torus manifold that has this dynamic, which is viewed here from above as a rotating yin-yang sign, if you'd like. Right. And so that's quite a different picture. And it's quite a different view of the universe, because now space-time is the source for spin, for Coriolis forces, for the magnetic fields, and now we can start to drive the whole equations of creation based on this space-time torque, generating even gravity and electromagnetic radiation. Because you see, now we have a direct balance equation. This is the next paper we're writing right now, is the balance equation that shows that there's a balance between how much space-time torque, how much force is applied on the system, and how much shearing that generates, and how much radiation the system outputs. So now you have a feedback between the gravitational field and the space-time torque. And that was the dynamics that I was looking for. If we look at the torus, from above, what's in the middle? Space, vacuum. The middle of the donut has a hole. This is where singularity would be in the center of a black hole. So at the center of the space-time manifold, where we would expect the Planck's distance at singularity, we find the vacuum state polarization. This is why the vacuum has polarity and structure, because space-time has angular momentum, is rotating, which generates acts of rotation that generates structure in the space-time manifold. And so we approach the center of the torus, we approach that point towards the Planck's distance, and we used group theoretical models to look into there and solve that point for subatomic particle. And when we were able to solve all the subatomic particles, okay, for that point, all the particles we observed, subatomic particles for that point, which were now linked in our mathematics to the space-time manifold for Einstein field equation for large objects, when we went to that point, the solution gave us a vector equilibrium. Okay? This is a solution given out of a set of mathematics that had nothing to do with my instinctive and logical thoughts that had brought me to believe that this had to be the geometry of the vacuum, the geometry of singularity. Yet the mathematics totally confirmed it. This all came together in a beautiful way that generates a full unified field theory in which the dynamics of space-time is that feedback loop between the gravitational field going in and the electromagnetic field going out, and the center vacuum structure, the singularity, which is the fractal space-time grid that defines that field equation. All put together, you get all the particles of subatomic particles and all the mathematics you need to solve gravitational fields, the electromagnetic field, the strong and weak force. Thank you. So there's still a lot of complexity built in. I think that complexity is going to really reduce when this is fully understood, because I believe we can make way with the strong and weak force. I think those are inventions of humans. They have nothing to do with reality. They have nothing to do with the atom. You see, what happened is they discovered nuclei of the atom, and they found that there was protons in it. Those are highly charged, positively charged particles. If you take two positive magnets and you try to push them together, you're going to get a repelling effect, right? Now, when they calculated how much force you would need to push these particles into a nuclei of an atom, those protons all squashed together that close together, they calculated the force you need to do that had to be extraordinary. And so they said, that can't be gravity, so we'll just invent a new force. We'll call it the strong force. It's strong. And what are we going to do? We're going to make it be mediated by gluons, because it's gluing everything together. Well, okay, that's one approach to physics, and then you can say, well, you know, it's there because we calculated it, but you didn't really ever experience it. You'd never even measured it. You just think it's there because you can't imagine how those protons could be together without it. Then they found the quarks, and they said the quarks are inside. You see, inside the protons, so they are squashed even smaller. So then they had to have an even stronger force. But they didn't want to add another force. I mean, that would look goofy, right? So they just said, well, that's the color force, and actually the strong force is just a residual force of the color force that's really strong in the middle. Well, if you make calculations for a black hole atom, and you calculate how much gravity there is at the nuclei level of a black hole that size, you have exactly the force you need to keep the atom together, to keep the nuclei together. You don't need the strong force. You're dealing with gravity in the vicinity of a singularity. You understand? And so now you can make away with that force. And so that starts to change your picture of the weak interaction and all this as well.
I would like to interrupt this presentation to give a little more details for the more technical audience. Here I'm describing the atom as a mini black hole. Many would say the atom doesn't have the mass necessary to be described as a mini black hole. However, in this presentation and in my research, I have come to conclude that the atom is interacting with a very highly structured dynamic vacuum, feeding it its energy potential and its density. And as we've seen in the presentation, the density of that vacuum is extremely large. I believe the vacuum is a highly structured, coherent energy that is feeding the atom and that is producing the dynamics that we see as particles and electron dynamics. In this view, then, the strong force becomes the gravitational force in the vicinity of a mini black hole produced by the vacuum structure. The electron is spinning at near the speed of light as a result of it being in the vicinity of the event horizon of that mini black hole. All this gives us a brand new picture of the physics of creation. Let's continue with our presentation.
What I'm bringing in is that, wait a minute, by modifying Einstein's field equation, we might be able to solve for all this and not need so much quantum theory, which is quite a change in the optics. This is one of the things that Einstein believed all of his life. That's why he was never keen on quantum theory. That's why people say that he dropped out after he wrote his field equation. He didn't really want to participate anymore. He believed that with his equation, he should be able to solve all the way down to the subatomic particle, and he actually got really close, I believe, at one time, because a French mathematician contacted him that was giving him solutions to his own equation that incorporated torsion. Torsion is a distortion of an object. If you apply torque to an object, imagine you have a 2x4, and you hold the bottom and you twist the top, you're going to get a distortion of the object. Okay, that's called torsion. And so this is Élie Cartan, thought that, maybe we could solve Einstein field equation just by describing the torsion or the distortion of space-time around a gravitational field. And he solved it. The thing is he solved it, and it gives the exact same answer as Einstein field equation. So everybody said, well, it doesn't teach us anything more, and it's more complex, so they dropped it. The only thing is that in order for something to distort, you have to have torque in the first place. And that they never went to. They never added the torque to the space-time manifold. If you are missing 98% the mass of the universe, okay, you most likely missed the source of force that is creating what you are observing. And I believe that source to be space-time torque. Okay, the force that spins a galaxy. Imagine if you had to build a motor, how many horsepower you would need to spin one galaxy with 300 billion stars in it. A lot of force. Imagine how much force you would be missing if you didn't account for that engine. Right? That would be like analyzing the wheels of your car, okay, and all its dynamics, its mass, its angular momentum, and everything, but omitting to add to your analysis the V8 engine that's spinning it. Now, when you look in nature, you can see these dynamics. Look at this. This is a galaxy, okay? And galaxies have galactic halos. Can everybody see this? It's like a very fade, big sphere around the galaxy. And when, when we look at galaxy, typically we only think of the galactic disk, right? And that's because in the galactic disk, there's the most amount of density because the sphere around a galaxy has a huge surface, so things spread apart, so it's not as easy to see. But there's actually more stars in the galactic halo around galaxies than in the galactic disks. And then here, you can definitely see a huge vortex going into the black hole at the center of the galaxy. We can't see the one below it because, these are very far away and we don't have that great of optics and so on. But we know that in general, there is always, or typically, two huge vortexes going into center of black holes. In the case of our galaxy, that vortex is, I believe, 3 on the north pole of our galaxy, if you're looking from our perspective, is 3,000 light years long. 3,000 light years long. This is, at the speed of light, it would take still 3,000 years to get to the end of the vortex. And it's filled with gases and high velocity dynamics and high energy dynamics enough that it's actually visible thousands and thousands of light years away from it. Imagine how much torque you need to produce that. Isn't that an obvious example of water going down the drain? Okay, now you'd say, well, wait a minute, when we see these vortices and we follow the particles, they're spitting out. Okay? Well, okay, if water is going down your drain, air has to move out of the drain for water to come down. That's the exchange. We only see the outside of the event horizon. We only see the radiating part of the event horizon. We don't see the space-time torque going into it to force the system to have angular momentum. And so the result is that we live inside a black hole. That's why it's black out there at night. Okay? And what we see inside that black hole are smaller black holes, smaller scale black holes, that we're on the outside of. So what do they look like? Radiating stars, radiating objects. Because we're on the outside, we're seeing the plasma Coriolis forces dynamics on the outside of the thing. We see the radiative side, we don't know about the contractive side, and that's why most of our physics is based on the radiation. But there's an exchange between the two, and this is the exchange I'm showing here, and that we calculated. These are very large objects, blazars, quasars. They're all being photographed to have these huge vortices. They're enormous. We see them at all scales. This is a quasar. So here you can see 10 to the 6 light years long is this vortex. That is 1,000,000 light years long. Okay? 1,000,000 light years long vortex. At the speed of light, 1,000,000 years to get to the end of it. And these things are spinning at near the speed of light when they arrive at the event horizon of the black hole. So very, very high torque. Big engines out there that are not being calculated. Now this is the different scale. Those are called microquasars. We find those even inside our own galaxy. And in this case, the vortex is only 3 light years long. So now you're starting to see the scalar dynamics, the scale change, the fractal nature of the division of space. From quasars to microquasars to collapsed stars or supernovae, we see the same dynamics, the same vortex. Look at this vortex dynamic on this pulsar, which is the result of a supernova explosion. Have you ever seen articles in a layman physics magazine where it says the death of a star explode into a supernova? Okay. We haven't ever experienced the death of anything. We haven't observed that. We really haven't. All we've observed is things changing state. Okay? For instance, I'm not talking esoterically here. For instance, people have all sorts of debate about if life continues after death or eternal or whatever. You don't need to be esoteric. Just take, what you got and extrapolate from it. You have a few billion atoms. There's a lot of cells. There's 100 trillion cells in a human body. And they're all organized in an organized matter. And then all of a sudden, they disorganize. Okay? However, all these atoms are still spinning. You haven't lost one. Okay? They're still out there. They're still spinning. In fact, you might be made out of the atoms of your neighbor. And your neighbor might be made out of your atoms. And so there's no evidence that things actually stop. Because if there is space-time torque going to singularity in each point, then there is angular momentum at all levels and things continue spinning no matter what. What I'm saying is that the friction that's out there is overcome by the space-time torque. So, and that makes it appear as a frictionless environment. So we don't see death. We just see things changing levels of organization, changing scales. And when we see a star exploding, right, they call it the death of a star. But when they focus on that same area afterwards, what do they see? They see a pulsar. Oh, that's nice. They just changed the name from star to pulsar, so the star is dead and the pulsar is born. Let me give you an example. If you were a camera inside a woman's womb, and this woman was pregnant, you would see life developing in that womb. And after 9 months, you would have probably a pretty good relationship with this life inside the woman's womb. all of a sudden there's a big earthquake in your world, and waters disappear, and there's an opening that opens in the little black hole at the end of this hip joint, and this being that you had a relationship with disappears through that hole. You would experience death. You would think this being is dead. The person on the other side experienced life, crossing the event horizon. Right. So what I'm saying is that our mathematics and our views have now shown us that actually pulsars and supernovae explosions are the result of stars when space-time is torqued into a certain radius, and it generates material inside, so that the Big Bang is only one of those events that generated the atoms of our universe, that atoms are actually being manufactured at the singularity of black holes. And that's the exchange of those atoms coming out, those vortices, as the space-time torque influence those black holes. And when those particles get out of there, they are stuck in the gravitational field of that black hole and accrete on the surface of the event horizon, as well as other atoms that are created by that black hole as it travels through space. And when it accretes too much material, it becomes unbalanced. There's too much radiation for the contractive torque force at the center of the system. The system slows down too much, and the instability generates an explosion. It blows up. What it does, it releases a layer of material so it can regain stability. And so that's what we see. And then it regains stability, and when it does, guess what? The radius is much shorter, the ballerina is brought as her arm in, so the thing spins way fast, like a pulsar. Okay? And then if it's fast enough, then we call it a black hole, and we say, look, the star made a black hole. And what I'm saying is, no, the black hole was always there. What we observe now is the dynamics of that black hole much closer to the event horizon, so we see the X-ray emission and all this stuff that we wouldn't observe before. By the way, all these things are X-ray emitters, from atoms all the way down to up to galaxies and so on. So so do you see how the picture is a little different? Now we start to see the universe as cycles in space. Okay, instead of start, stop, start, stop. And you start to see that maybe, just maybe, that's how our universe was created. An enormous black hole that became unstable and blew out a certain amount of its ergosphere, a certain amount of its plasma, which generated all the rest of the stuff we see today. And that those cycles most likely go on and go on and go on forever. Even the dynamics of the Earth plasma, like the dynamics of the Earth stratosphere and the way hurricanes and weather systems move around the Earth, obeys those conditions. That is, the weather systems go from the North Pole down to the equator and then back up. And from the South Pole up to the equator and then back down. They don't cross over. And so on. So there is those dynamics, those plasma dynamics are seen at all levels. In the sun dynamics, we see the exact same pattern, that double torus pattern, in the dynamics of the plasma around the sun. So, and what we see in these dynamics, we see Coriolis force, and in the center of these vortices, what do we see? We see a black spot. We call it a sunspot. And typically we've been told that sunspots are surface events, and I debated this for 15 years, and finally they're finding out that they're not. They're vortices going towards the middle of the sun. Because what you're seeing in a sunspot is a vortex, Coriolis forces going towards singularity, and that's why they're most commonly matched by another one on the exact opposite side, right, that meets at the center. So those dynamics between the sphere dynamics and the geometry of space that we saw earlier, between the field dynamics, which would be the sphere around each tetrahedron, and the structure of the vacuum that generates it, that maintains it, we can see that these dynamics are actually present at all levels, even at the biological level, as I was saying earlier, and even you got here by going through these vectorial array dynamics in the womb of your mothers. I point that out all the time. It's like, you want a proof of the fractal nature of space? Well, have you not noticed? People take that for granted. People come out of other people. It's an amazing thing. They do. I mean, I have pictures of my mom with her grandmother, with her grandmother, and like the cousins and everything, and you can see the fractal link of all the mothers, you know, through space-time. I mean, it's freaky. People coming out of other people. I mean, it's pretty obvious it's a fractal structure. And so, when you look at the way it happens, even the woman's womb, well, the first cell divides into two, and then the two into four, and when they do four, they arrange into a tetrahedral array. And then these four divides into four again, into two each, making 8, and those 8 arrange in a star tetrahedron array. In all of this, you're starting to see, in any case, that this very fundamental geometry is actually how you emerge into this world. You went through that structure in order to get here, and you went through it through the molecular interactions of water. And if we look at what really generates this placements of molecules or cells, well, there's a strand of code inside the nuclear cell that we call the DNA code. And this DNA code is really, you know, an interesting thing, because if we look at the dynamics of that code, it has that spiral kind of torque field look to it. And assuming that these energy levels for cells are correct, and that we can actually describe the cells as like mini black holes interacting things, we would see that at the nuclei, we would see that at the center of the cell, we would see these spiral-like structures. But and you know, there is a lot of code in your body for you to be here. The complexity is outrageous. I mean, seriously outrageous. If you take the DNA that's in your body, in each cell, there's approximately 6 feet of DNA. And if you put all these strands of DNA end to end, you could wrap it around the world 5 million times around the world, 4 to 5 million times around the world. 4 to 5 million times around the world. That is inside your body right now for you to be able to function. So that all the cells know what everybody else is doing, and everybody is organized, and all the information is moving through, and all this is happening because there's a fundamental codonic interaction of the proteins that permits it. And guess what that code is based on? Well, the codon structure of DNA are based on a 4 to the third, relationship, which is 64 codon possibilities of combination. I find it interesting that this, 64 possibility codes that generates the amino acids of DNA and so on, matches what we call the affine connection metrical space that Einstein used to produce his field equation, the space-time manifold. It's called the affine connection, and it has a 64 element metric that generates a component for the space-time manifold structures. So then we have a direct link here between the space-time information, the space-time torque, and the way DNA is. Like DNA is like the transducer from space-time information moving through into the world and gathering information. You're like a probe for space-time looking back at itself from the outside and gathering information about its existence. Now, please don't go to your shrink and say, I think I'm a space-time probe, because you might get in trouble. But this is a very exciting kind of view that, like, we're starting to see the relationship between the space-time structure and the biology and how biology moves through things.
Thank you for joining us today in Crossing the Event Horizon. Nassim Haramein's research is supported by the generosity of the public. To directly participate in this most crucial work, see our website for more information on how you can stay involved by visiting www.theresonanceproject.org. Thank you for continuing to spread the word about this exciting work and recommending this DVD to your friends and family. Be sure to watch the special features portion of this DVD.